must be a leak somewhere. Ah, these valves are all rusty. Another job for later. What's your problem?
Stella, we're having an argument here over Jodie's experiment. I just want them to eat this onion. No way. It's raw. It tastes disgusting. And it'll make your breath stink.
It's got my eyes watering just looking at it.
Yeah, but you're happy enough to eat it if I give it to you cooked, like this?
Well, that's different. When you cook it, all the acids and the vapour that sting your eyes have drained away.
Yeah, and you can't uncook an onion. You can never make it taste raw again. Stella, why does a raw onion taste so different from a cooked onion?
I'm onto it. It tastes different, it looks different, and it smells different. It's almost like the onion has changed into a completely different substance. Well, in many ways it has, because the cooked onion is chemically very different from the raw one. Talking of cooking, just in time, perfect. Another chemical reaction has just happened here.
Chemical reactions are useful in cooking. They help improve the taste of food. Cooking and chemistry have quite a bit in common. The starting materials in a chemical reaction are called the reactants. These react with each other to form a completely new substance, the product.
As you can see, products have very different properties to the reactants. This cake is a lot firmer, tastes a lot nicer than the individual reactants. It's a different colour too.
Not all chemical reactions need heat energy to make them happen. Take some bicarbonate of soda, add a little vinegar, and watch. It's another chemical reaction. This time, one of the products is a gas, enough to inflate a balloon. Without chemical reactions, it wouldn't just be our food that would be boring.
Come on, Debbie, get stuck in! I think there's definitely room for improvement down there.
I get knocked down, but I get up again. You're never gonna keep me down. I get knocked down, but I get up again. You're never gonna keep me down.
What's all this then? White socks, white shirts, white shorts. It's not a particularly practical colour for a kit, is it?
Boring.
But we've only just got one, and we're not allowed to buy a new kit, so we're stuck with the white.
I think I might just be able to help you. Let me have a think about it. Bruce!
We can choose from a huge range of colours for our clothes, but it's not always been like that. In the past, most colours were difficult to obtain. For instance, one yellow dye was made using cow's urine. I've come to meet Carol, who's a bit of an expert on dyes.
Do you know, I don't think the team would be into us dyeing their clothes in urine.
I thought so.
A bit smelly, actually.
Very smelly.
Surely there must be easier ways of getting colours now.
Well, there are actually. Last century, chemists came up with ways of making colourants using chemical reactions.
Say if I wanted to dye these shorts bright orange.
Right, well, first of all, glasses and gloves. Then what we can do is we can take two chemicals and we can mix them together, they'll react, and they'll produce an orange dye.
So, these two reactants have no colour whatsoever, and the product is an orange dye?
Yep.
Wow! Right, we've got a lot more orange dye here. Time to dye the shorts.
Or should I dye the socks or shirts?
I get knocked down.
Now, that's starting to look better.
So, can we use chemical reaction to create any colour I want?
Any colour you want, thousands of them. Choose one.
OK, so can we dye their socks yellow?
No problem. We don't have to actually make dyes each time. What we can do is we can actually buy dyes that have been made by chemists using reactions like the one that we used earlier to make the orange dye.
Right, well, there's loads to choose from. Let's try this one.
This time, with this ready-made dye, we need another reactant.
In this case, what we need to do is we need to have another chemical for the dye to actually stick on the fabric. Sodium chloride.
Ah, now sodium chloride is salt like you have in your chips.
OK, let's give them a choice in yellow.
So that just leaves us one more colour to choose. So I think I'm going to dye the shirt blue. That should do it.
Now to finish them off.
Wow, you're looking a lot more colourful now. What do you think?
It's better than white. It's a bit bright.
You're going to have to decide what colour you like the best.
So what do you reckon then?
They're all right. But could you do us one in tartan?
So, colour, taste and texture can all change in a chemical reaction. But I'm going to investigate another property, mass. These pieces of iron wool have equal mass. The scales balance. But what do you think will happen to the scales if I burn this one?
It's going to get lighter, isn't it? Burning it's going to turn it into ashes and it won't weigh as much. Yeah, it's definitely going to get lighter because the iron wool will burn off. The smoke.
I think you're both wrong. It's going to stay exactly the same because the iron isn't burning. It's just getting red hot.
Its mass has increased. What's going on? Where's the new stuff come from? This time, I'm going to burn the iron in a sealed container.
When the iron burns in air, the heat causes the reactant, the iron wool, to react with oxygen in the air. So now there's less air in the bell jar and the water level rises. It's another chemical reaction called combustion. And we can test. Watch.
No oxygen gas in there anymore. All the oxygen has combined with the iron.
In the air around the heated iron wool, the oxygen particles are whizzing about. They're on the lookout in case there are any available particles to join up with. When the oxygen particles come into contact with the hot iron particles, they readily combine with them. The result is a completely new substance. Iron oxide.
These burnt remains contain both the original iron plus the oxygen, so have a greater mass than before the iron was burnt. But combustion isn't the only way to oxidize iron.
This looks like it's going to be an interesting investigation. I'm meeting Alex aboard her ship.
Hello, Alex.
Hi, Femi. Welcome aboard.
Thank you.
To find out about a very unusual example of a familiar problem, rust.
I have to wear this hat, I'm afraid.
Right, thank you. So, I hear you have a bit of a rusty problem.
We do indeed.
So, where is it?
It's down here. The world's first engine-powered submarine called the Resurgam, which sank back in 1880.
But what sort of condition is it in?
Well, that's what we don't know. It's made of iron, and iron rusts or corrodes, especially in the seawater in this sort of environment. So we're surveying it to find out what sort of condition it's in.
All over Alex's ship, you can find lots of examples of rust.
Rust is the product of a chemical reaction. The iron reacts with the oxygen in the air or in the seawater. It's a form of oxidation. It also needs moisture, and there's no shortage of that on a ship, and it leads to corrosion like this.
I don't have to get wet to see the Resurgam. The camera on the front of the remotely controlled Explorer allows us to see everything that's down there. Through the murky water, we see the conning tower. The sub's covered in barnacles. But look, it hasn't rusted away. It's actually got bigger. Back on deck...
Look at this.
What is that?
Alex has something found on another shipwreck. Most of this is rust built up over hundreds of years on the seabed. Hopefully, the original object is still in there.
Well, I need to get my delicate tools. This one might do it. Yes. There you go. Can you see the object in there? There, can you see? That's an iron shot. When I touch it, you can feel it's hard.
And that's the rust around there.
That's the rust around there.
Amazing. Can't wait to see what's on our sub down below. Can we take a look?
Yeah, let's dive.
I want to see if I can bring something up from the resurgam so we can see what sort of condition it's in. But first, I've got to learn how to control the underwater Explorer.
Doing it like the way I drive, Alex.
There you go. You're now moving parallel to the sub. Oh, that's good.
Oh, no, look, I think there's something there.
Look, can you see? You have to go forwards. Yeah. See, look, it's round. Can you see the outline?
Excellent! I can't believe it! Ah!
We get some divers to go down and
we can pick it up.
Yeah, we'll get a survey and pick it up.
Let's go!
I have no idea what I found.
Oh, thanks. So, this has been lying on the sea floor for more than 110 years.
Yeah, that's right. It's a porthole. It's one of the portholes from the conning tower. Fantastic. It's in really good condition. I mean, it's marvelous. You can still even see the glass in the middle of it.
A 120-year-old porthole covered in rust. Beat that, Stella.
Actually, Femi, I think I can. How much iron do you think becomes rust in the whole of Great Britain in just 1 minute? This much? This much? No, this much. About 750 kilograms of iron become iron oxide. Like iron, most metals react with water and oxygen in the air to become oxides. But some metals react more vigorously than others. Like the metal sodium, for example. Sodium reacts so vigorously to even the tiniest amount of water vapor in the air that it has to be kept in oil. Other metals, like the silver used to make this knife and fork, hardly react to anything at all, so it's safe to put them in your mouth. It's called the reactivity of metals, and Femi's onto it.
Scientific investigations can be ever such hard work.
To investigate the ways different metals react, I've been told I should meet Alex. There's only one way to keep up with Alex. She's one of Britain's top swimmers.
Yes! Oh, Alex, you're a proper swimmer.
Well, yeah. Well, surely the reactivity of metals, different metals, isn't that important to you?
Well, actually it is, because if I didn't have the metal I've got in my body, then I could both fall apart.
What on earth do you mean?
Well, last year, before I was hoping to swim in the Olympics, I was in a really bad car crash and I badly broke my legs. To put the bones back in the correct place, the surgeons had to put metal implants in them.
That sounds terrible. But by putting metals inside your body, isn't there a problem with those metals reacting with all the chemicals in your body?
Well, if you put any old metal in, I'm sure there would be, but whatever they've done with mine doesn't seem to work too badly.
Well, it looks like you made an excellent recovery, but I would love to find out what sorts of metals they used.
Well, I'll leave you to it.
So what metals would they have used for Alex's implants? Some metals react more with oxygen and water than others. You can use this knowledge of how different metals react with oxygen or water to form a kind of league table of reactivity. It's called a reactivity series.
At the top are the most reactive metals like potassium and sodium. And as you go down the reactivity series, you reach the metals which are least reactive, like silver and gold.
Well, they had to put metal in me. I know exactly where in the reactivity series I'd like it to be. Gold, right down there at the bottom. I'm going to go to Alex's hospital to see if I'm right.
Them bones, them dry bones.
Come in, Femi.
Hi, Sandra.
Hi.
Them bones, dry bones, them bones.
I'm just having a look at Alex's x-rays now after her surgery.
Oh yes, well, I can see the bone down here, and the lighter bits, are they bits of metal?
Yes, this is the metal that holds the bone. You can see her foot. This is her knee, the piece of metal there. And these are the screws that hold them all in place while her bone heals.
Wow.
Come and I'll show you. And see what we have here. A model skeleton.
Glad you said that.
And it shows us ways in which we can use metal in surgery to heal joints and replace joints that have been injured or diseased.
What's this?
That's what we call an artificial knee joint.
Now, why don't we use gold for the implants? Because gold is at the bottom of the reactive series.
That's right, it's got very low reactivity, and we do use it in the body. Look here, these gold fillings doesn't react with the food and the saliva. Gold is a soft material, and we wouldn't be able to use it to replace artificial knees and hips, because for an artificial joint, we need a strong material to take the stress.
So what metal do you use then?
Well, the implants that we've been seeing are made of a metal called titanium.
Hold on a minute, titanium.
That's even higher in the reactivity series than gold.
But that's quite good, because it's reactive, and it reacts with the oxygen in the air to form a barrier layer of titanium oxide. And we know that bone cells like to grow on this surface, and that makes it a good material for bone replacement.
And because this oxide layer forms a stable and protective barrier, it stops any other chemical reactions from happening and allows Alex to get on with her swimming.
Well, the pressure valves are a bit more secure now, but I've found that leak. While I fix that, here's one for you.
Whoa, they've all gone different colours.
Looks like a chemical reaction to me.
Yeah, but it's only one reactant. Well, there has to be at least 2 reactants in a chemical reaction, doesn't there? But the glasses are all empty.
Perhaps the glasses are made of 3 different materials.
No, they're all identical. And the glass can't be a reactant, otherwise all the products would be exactly the same. There must have been tiny amounts of different chemicals in each of the glasses.
Reaction. This time, one of the products is a gas, enough to inflate a balloon. Without chemical reactions, it wouldn't just be our food that would be boring.
Come on, Debbie, get stuck in! I think there's definitely room for improvement down there.
I get knocked down, but I get up again. You're never gonna keep me down. I get knocked down, but I get up again. You're never gonna keep me down.
What's all this then? White socks, white shirts, white shorts. It's not a particularly practical colour for a kit, is it?
Boring.
Another job. For later. What's your problem?
Stella, we're having an argument here over Jodie's experiment. I just want them to eat this onion. No way. It's raw. It tastes disgusting. And it'll make your breath stink.
It's got my eyes watering just looking at it.
Yeah, but you're happy enough to eat it if I give it to you cooked, like this?
Well, that's different. When you cook it, all the acids and the vapour that sting your eyes have drained away.
Yeah, and you can't uncook an onion. You can never make it taste raw again. Stella, why does a raw onion taste so different from a cooked onion?
I'm onto it. It tastes different. It looks different. And it smells different. It's almost like the onion has changed into a completely different substance. Well, in many ways it has, because the cooked onion is chemically very different from the raw one. Talking of cooking, just in time, perfect. Another chemical reaction has just happened here.
Chemical reactions are useful in cooking. They help improve the taste of food. Cooking and chemistry
Must be a leak somewhere. Ah, these valves are all rusty.
have quite a bit in common. The starting materials in a chemical reaction are called the reactants. These react with each other to form a completely new substance, the product.
As you can see, products have very different properties to the reactants. This cake is a lot firmer, tastes a lot nicer than the individual reactants. It's a different colour too.
Not all chemical reactions need heat energy to make them happen. Take some bicarbonate of soda, add a little vinegar, and watch. It's another chemical reaction.